Join us in this tour around Bomag's world of compaction. Greater social mobility and growing traffic volumes are imposing higher loads on our road networks. Day and night, this traffic moves along our highways and over our bridges, sewers and pipelines. Rail tracks and airport runways must also be built to withstand increased loads. Today, Bomag is providing new solutions to improve quality on earthworks, highways and civil engineering projects for higher levels of stability and long-term performance of compacted soil and asphalt. Compaction reduces the air voids in a material, increasing the internal friction between individual particles and producing higher stability in the material skeleton. The aim of soil and asphalt compaction is to provide high load-bearing capacity, good stability, low permeability and a good surface finish for a long, low-maintenance service life. Poor compaction produces low load-bearing capacity, causes settlement and deformation and increases the risk of frost damage. All construction sites are different, and for every application, Bomag has the right model in its range. Here are some examples. Let's look at the various types of compaction equipment. Vibrating tampers. Designed primarily for compaction in trenches and in confined working areas. Tampers are suitable for use on a wide range of soils and granular materials. Vibrating tampers are sometimes used to compact asphalt, for example on highway patching work. Vibrating plates. These units are best suited for use on granular materials and asphalt. Available as single direction models from 40 to 180 kilograms and as reversible plates, weights ranging from 120 to 750 kilograms. Typical applications include trench reinstatement, backfill, paved areas and patching. Light and medium duty plates used to compact asphalt are equipped with water sprinkler systems. Hand-guided double vibratory rollers have operating weights between 500 and 1500 kilograms. The output of these rollers is higher than tampers and most types of plate compactor. Highly maneuverable multi-purpose compactors, mainly used on cohesive soils, can be supplied with remote controls for use on difficult or hazardous applications. Equipped with water sprinkler systems, hand-guided walk-behind rollers such as this are suitable for small-scale asphalt work. Ride-on tandem vibrating rollers have two drums and feature hydrostatic travel and vibration drives. Tandem rollers are often used to compact asphalt and are fitted with water sprinkling systems. Tandem rollers with operating weights between 6 and 12 tons and working widths from 150 to 213 millimeters are suitable for medium to large contracts. These models feature automatic vibration control, which switches vibration off when stopping or reversing to avoid rippling or unevenness on the surface layer. Large tandem rollers are available in split drum versions. Split drums minimize the risk of shoving or cracking when turning or rolling on bends. Large tandem rollers can be articulated or pivot steered depending on design and application. Both types have specific advantages for various compaction and rolling operations. Single drum rollers feature front vibrating drums and rear driven tires. They're designed for soil and rock compaction, where high climbing capability can be as important as compaction performance. Operating weights are from 3 to 25 tons. Single drum rollers are generally used on medium to large-scale applications. Depending on soil type, self-propelled rollers are equipped with either pad foot or smooth drums. DH and PDH high climb models have been developed for landfill and dam construction work. Equipped with Bomag ASC anti-slip control, these rollers have a climbing ability of up to 55%. Now let's see how we compact different material types. The material always determines the choice of compactor. Soils can be classified as either cohesive or non-cohesive. With cohesive soils, the particles adhere and stick together. Only cohesive soils such as clay and loam can be kneaded and formed into a ball. Cohesive soils are compacted by the kneading action produced by a pad foot drum and vibration. The opposite applies with non-cohesive soils. Here the particles are bigger and do not stick. Kneading is impossible and the particles fall apart. These soils are best compacted with vibration. This reduces the friction between the particles and results in higher density. These are the different types of soil. Clay. Clay soils feel soapy and stick to the fingers. Silt feels soft and floury. Dry particles can be easily crushed. Sand has individual particles smaller than the head of a match. In most cases they can be seen with the naked eye. Gravel consists of particles of various sizes, from a match head to a golf ball. Rockfill consists of boulders of different sizes and strengths. Some rocks can be crushed by pad foot rollers. The layer thickness plays a big role in compaction. Thickness depends upon the type of material and the effectiveness of the compaction equipment. To compact thicker layers, the power requirement is higher and heavier rollers with higher amplitudes will be needed. Lighter compaction equipment is the right choice for thinner layers and easy to compact materials. To adapt to different types of soil and rock fill and different layer thicknesses, single drum rollers are equipped with 2 frequencies and amplitudes. In soils, an important influence on compactability is the moisture content. Water acts as a lubricant between soil particles. It allows easier relocation of these particles, and for the best compactability, the optimum moisture content should be present. The optimum moisture content is usually determined in the laboratory using the Proctor test. The maximum dry density and optimum moisture content are determined by applying constant compaction energy. The Proctor value is often used to assess compaction density on site. Every soil type exhibits its own Proctor curve. Now let's look at asphalt. Asphalt is a hot mix of selected aggregates and bitumen produced in a mixing plant. It can be laid by paver or by hand. Asphalt is used in road construction for wearing, binder and road base courses. Compactability. The compaction required is primarily influenced by the composition and temperature of the asphalt. Easy to compact mixes contain smoother particles or natural sand aggregates. The stone content is less and the binder has a lower viscosity. Asphalt mixes for highly trafficked areas are normally more difficult to compact. The aggregate is mainly angular, the stone content is high, as is the binder viscosity. The mix temperature. Temperature has a major effect on the compactability of a mix. At high temperatures, compaction is assisted by the lubricating effect of hot bitumen. This helps to reposition the aggregate. As temperature falls, the increasing viscosity of the binder must be overcome. The lubricating effect decreases. Temperature checks are therefore very important. The most favourable temperature range for compaction is between 160 and 100 degrees Celsius. In the lab, the Marshall test is used to analyse samples from each type of mix. This sample is compacted using a standard compaction force. It provides a reference for the compaction achieved on site. Compaction methods. Static compaction is used on easy-to-compact mixes, thin layers and finish rolling. A tandem roller used without vibration compacts with dead weight. Compared with vibratory rollers, compaction efficiency is low. Pneumatic tired rollers use static compaction principles. Compaction performance depends on the dead weight, the tire pressure and the rolling speed. Dynamic compaction. Tampers compact by impact force. The high pressure and shearing force produced by the tamper foot results in repositioning of the particles into a denser fit. Vibratory compaction with rollers. The dynamic forces generated by the vibrating drum move individual particles, reducing friction and, together with the dead weight of the roller, produce compaction. Vibration is produced by a rotating eccentric weight. Its speed determines the vibrating frequency. Two eccentric weights are used in reverse directions to provide two amplitudes. So, what are the key factors influencing compaction? They are static linear load, vibrating mass, amplitude and frequency. First, static linear load. Static load is a good measure of the compaction potential of a roller. A high static load implies better performance at depth. Tandem rollers have linear loads between 10 to 30 kilograms per centimetre. Single drum rollers range from 20 to 80 kilograms per centimetre. Next, vibrating mass. Vibrating mass is the machine weight which is excited by the vibrator shaft. The higher the vibrating mass, the higher the compaction effect. Finally, frequency and amplitude. The optimum performance for vibratory compactors normally occurs in the frequency range from 25 to 60 Hz. The height of amplitude influences performance at depth. A large amplitude provides more compaction energy. Most tandem and single drum rollers are designed with two frequencies and amplitudes. Tandem rollers have frequencies between 35 and 55 Hz with an amplitude range from 0.2 to 1 millimeter. Single drum rollers operate with frequencies between 25 and 40 Hz, since this range provides the best result on soils. Because soil layers are thicker than asphalt layers, single drum rollers are designed with amplitudes between 1 and 2 millimeters. Now a look at rolling speed. In vibratory compaction, rolling speed is critical. Increasing speed reduces the compaction energy per surface unit. Higher speed also increases the distance between impacts. On asphalt, this can produce surface rippling. Recommended rolling speeds are 1 to 4 kilometers per hour on soil, 2 to 6 kilometers per hour on asphalt. Now let's look at automated compaction using variomatic and vario control. These are intelligent systems which calculate the force needed for compaction and optimize the roller output in relation to material stiffness. Variomatic uses two counter-rotating eccentric shafts to generate directed vibration and is used in tandem rollers. Variomatic produces increased uniformity, improved evenness and better surface finish on asphalt. Vario Control is Bomag's automated system for single drum rollers. With Vario Control, amplitudes up to 2.5 millimeters and centrifugal forces up to 500 kilonewtons are generated. 3 eccentric weights are mounted on concentric exciter shafts. The weight in the center rotates in the opposite direction to the outer weights. Any direction of vibration between horizontal and vertical can be selected by turning the complete vibrator unit. In addition to automatic mode, both systems offer the operator a choice of manual force and direction settings. A major benefit of automated compaction systems occurs when compacting on bridges or close to buildings. By selecting horizontal vibration, the load applied through vibration is minimized. Now let's look at compaction testing. On soils and unbound granular materials used in earthworks, standard compaction tests determine density or load-bearing capacity. On site, various tests are used. On cohesive soils, coring can be used, whereby a steel cylinder is pressed into the soil. The density is then determined on the basis of soil mass and volume. For most soil types, substitution methods are used to calculate density. Here, the volume of the soil sample is replaced by a substitute material. This is a bentonite substitution test. Compaction can also be tested by measuring the load-bearing capacity of the soil. With this test, the settlement of the soil under load is measured. With the plate-bearing test, the load is applied in stages. Settlement is shown on the gauge. From a pressure settlement graph, the deformation modulus is determined. The light drop weight provides a quick test. With this instrument, the dynamic deformation modulus is determined from impact loadings. Compaction can be indirectly tested by the standard penetrometer test, where the number of impacts are recorded. On asphalt, compaction is tested by measuring the density of the material. On most contracts, core sampling is specified. This is used to determine the degree of compaction, the air void content and the laid material thickness. A nuclear gauge allows quick testing without destroying the pavement. The gauge calculates density by measuring transmitted and received radiation levels. The launch of the Bomag Terrameter was a milestone in the development of compaction test methods. The Terrameter optimizes the use of compaction equipment and provides surface documentation of soil compaction. For large-scale projects, the Bomag BCM Compaction Management and Documentation System was developed to supplement the Terrameter. It assists the roller operator with graph format visualization of omega compaction values and helps contractors and engineers to monitor compaction work. Now we'll see how Bomag continues to set the pace with its research and development of application solutions. Here, Bomag has modified standard padfoot drums to enhance their kneading, pushing and crushing performance. Triangular teeth with cutting blades between are highly effective for crushing brittle rock materials. Mounting these hydrostatic plates to a single drum roller increases machine utilization and speeds up compaction work. The efficient performance at depth of a single drum roller is combined with the efficiency of the plates at the surface, giving more compaction with less passes. Asphalt Manager was developed for variomatic tandem rollers. In providing a new test for stiffness on asphalt, Asphalt Manager continuously optimizes roller performance and, at the same time, monitors changes in compaction. Asphalt temperature is permanently monitored and displayed in analog form, together with the EVIB stiffness value. Bomag, setting the pace in compaction.